All right, folks, welcome to Regression Analysis. Once again, in the previous lecture, we stopped at maximum likelihood, and so we'll continue from there, okay? Estimation issues, we talk about OLS estimation and maximum likelihood methods of estimation. From there, we move to goodness of fit, where we look at how our regression has been able to explain the variation in the dependent variable y. So remember, we practice this under simple regression. The idea is the same, so I don't plan to spend much here. R squared is our coefficient of determination. Okay, that's another name for R squared, coefficient of determination or goodness of fit. It tells us how our model was able to explain the variation in the dependent variable. Okay, coefficient of determination. We will have some examples to interpret, but I'm sure we did some under simple regression. Okay, coefficient of determination. That's our R squared. Okay, goodness of fit. How much of the variation in Y is explained by the regression model, or taking all the x's together, how powerful were they in explaining, okay, Y, okay. And then here we talk about the assumptions under the multilinear regression model. Remember, these assumptions gives us the desired properties of our estimators and enable us to, rely on the regression framework. So the first one is linear in parameters. Like I said, linear in parameters means it must be linear in the betas, beta 0 all the way to beta k. Okay, and that is it. Even when we have nonlinear components like x1 squared and so on, we still call it a linear regression model as long as it's linear in the parameters. So something like this is not linear in the parameters. Let's say if you have something like x1 and then x2 are our variables, there's an e raised to the power epsilon. So our error term, so let me put something here like beta 2 and then put something here like beta 1 and then put something here like our beta 0. So something like this is not linear in the parameters, okay? But this will be something we call intrinsically linear. Later on, we will learn how to transform nonlinear model into a linear one. This is intrinsically model. For those who cannot wait, we'll just take natural logarithm of both sides, and we have ln of beta 0 plus beta 1 ln of x1 plus beta 2 ln of x2 plus epsilon, because ln of e just knocks off. Then we have linearized it, okay? You can easily redefine the constant here to be alpha 0 and so on. Okay, let's move on. So that's linear in parameters. Our second assumption is no perfect collinearity. In other words, in the sample and also in the population for that matter, none of the independent variables, okay, none of the independent variables is a constant, and there are no exact linear relationship among the independent variables. If you have independent variables, say x1, sorry, let me get my eraser. If you have independent variables like x1, x2, x3, you don't want, say, x1 to be a linear combination of other regressors. We don't want that. Or maybe x1 is equal to twice x2. We don't want that, okay? So none of the independent variables should be a constant. Remember, beta 0 captures all the constants. So we don't want any of the x's to also be a constant. Otherwise, it becomes absorbed by beta 0. So none of the independent variables is a constant, and there are no exact linear relationship among the independent variables, okay? So this assumption rules out perfect collinearity. We call it no perfect collinearity. Otherwise, we also know linear algebra. We cannot invert the X transpose X matrix. Okay, we cannot find the inverse of this. And remember, beta hat depends on this in the matrix framework. Okay. So if an explanatory variable is a perfect linear combination of other explanatory variables, it is superfluous and may be eliminated. Okay, like I said, constant variables are also ruled out because they are perfectly related to the intercept. Okay, now we are not saying x1 and x2 cannot be related. Covariate or regressors are always related somehow. So this is the point here. The assumption only rules out perfect collinearity or correlation between explanatory variables. Imperfect correlation is allowed, okay? Okay, so for example, this is also not allowed in a regression to have this variable plus this variable, they sum up to 1. Okay, so they are kind of perfectly, there's exact linear relation between them. So one of these two must be dropped. Okay, later when we meet in class, I will show you using the computer software why this is not allowed. You would see that software will not be able to estimate beta 1 and beta 2 at the same time unless you drop one of them. Okay. So our third assumption, which you are familiar with, the zero conditional mean, I explained this in a simple regression. We say that the value of the explanatory variables must contain no information about the mean of unobserved factors. Okay, the value of the explanatory variables should contain no information about the mean of the error term. I told you students tend to understand a watered down version that the error and your regressors should not be related. That's what students tend to usually understand. But this assumption is stronger than this one. This is a watered down version which students tend to appreciate. So your regressors and the error should not be related, but more precisely, the regressors should contain no information about the mean. Okay, I'll see if I will throw more light on that. Okay, maybe let's go to the simple regression framework. Let me go to share a whiteboard. Let's say we have our return to schooling equation. These are wages, and this is beta 0 plus beta 1 education plus your error term. Okay, now let us assume that ability, people's ability or intelligence is left here because we have no way of measuring ability precisely or correctly. Okay, people's ability or intelligence. You can use GPA, you can use some test scores, but it's actually not capturing ability. Why do I believe ability is in the error term? Because I cannot observe it. But why am I even thinking that ability belongs to this equation? Why? Because people's ability or intelligence actually affects their productivity and therefore affects their wages. Once they have high ability, it shows, the data shows, okay, evidence shows, and it's not difficult to believe that more high ability people will have more wages, okay, ability or intelligence. It turns out also that this ability also affects education because people with higher ability are able to get more education. Now, I'm saying ability can be in the error term because ability affects wages, so it is relevant. I cannot think about fertilizer here. Fertilizer cannot be in the U because fertilizer doesn't affect wages. So you can't get up and say anything at all is in the U. No, it must make sense. So you can't say fertilizer is your pesticide. That has nothing to do with wages. But we know ability affects wages. So once ability is not included here, like beta 2 ability, because I cannot observe it, then I've by default left it in the error term. Okay, now I'm saying that my regressor is related to the error term. Why? Because ability affects education. If you have high ability, you can get a degree in statistics, get a master's degree, get a PhD. So ability affects education. So once ability is the error term, then I have the covariance between a regressor and my error term not being 0. So that assumption is violated. But more strictly, we are saying that the regressor is having information about the mean, okay, of the error term. Okay, that previous assumption is zero conditional mean assumption. So this is what exactly it means, that the mean of our error term, let's say the term in the error, we think of it as ability and X as education. Think of this as our U and think of this as our S. We are saying that it's not 0. In other words, the average value of ability depends on education. Okay, or education is able to tell us about the average ability in the data or population. So that's throwing some light on that assumption. Okay, excellent. You can always ask more questions in class. Okay. Now let's go to something very important. We have praised multiple regression as an improvement on simple regression because we are able to add more regressors which otherwise would have been left in the error term and could cause problems, okay? Can you just be adding any other variable? Can you just be adding regressors? This ends at beta 3x3. Can you just add beta 4x4, beta 5x4? Can you just be adding any variable at all? No. So what are we going to learn on this slide? Including irrelevant variables in a regression. You cannot just be adding any variable at all in a regression. What you add must be relevant. What do I mean by irrelevant? For example, in the returns to schooling, my wage is assumed to depend on my education, okay, my level of education. Think about it. Can my sister's education matter in my salary? My sister's education. Such a variable is irrelevant. My sister's education doesn't determine my wage or salary. So this is an example of an irrelevant variable and should have no place here. Now we are going to learn the consequences. What happens if you keep throwing in irrelevant variables? Okay, we are saying that assuming x3 is irrelevant. In other words, beta 3 should have a population value of 0. It is irrelevant in this equation. So beta 3 is actually 0, means it doesn't belong here. Because the population value is 0, when we estimate beta 3, the expectation is also 0. So there's no problem in terms of unbiasedness of our beta 0 hat, beta 1 hat, beta 2 hat. But there could be problem with the variance, okay, variance of your betas, beta hat, because you have included an irrelevant variable which can easily define your new error term can be thought of as this, U plus beta 3 x3. Okay, you can think of this as your new error term. And that means it's not only U, which is your error term, something has been added. So there is a danger that it may increase the sampling variance. In other words, the variance of the estimate. And what does that mean? It means that you have noisy estimate. Okay, you are a statistician, you know what it means by higher variance. Higher variance means noise. Okay, so you can be asked that what's the consequence of including irrelevant variable? These are your answers. 1, unbiasedness of the regression coefficient is not affected once the variable is irrelevant. You say, however, the consequence is that it may increase the variance of the estimate, variance of the estimators, I beg your pardon, or sampling variance for sure. Okay, I hope that is clear, including irrelevant variables. What if you omit a relevant variable? What's the consequence? You omit a relevant. Here, you included something which is irrelevant. Okay? You included something which should not be included. Now, what if something should be included, but you rather left it out? What are the consequences? Okay, let us show the consequence of omitting something which shouldn't be omitted, should actually be part of the model. This is how we go about it. This model, we call it a true model, assuming that what the right thing to do is to have X1 and X2 in the model. But you made a mistake. Either you did not observe X2 or you didn't know, and you went ahead to just run the model with only X1. So you have omitted a relevant variable X2. We are assuming X2 is relevant because we are assuming this is the true model in a population. When you make a mistake and run this one, in other words, you run a simple regression instead of the multiple regression, then what are the consequences? What are the consequences? Okay, what are the consequences? I'm going to update this slide. It doesn't look nice here. If you put beta tilde, it is assuming you have already estimated it. But so we can do something like y. Okay, y is equal to alpha 0 plus alpha 1 x1 plus the error term, let's say v. We already use u here. We already use beta here. So just differentiate a little bit. Okay. So you are supposed to add x2, but you omitted it and you just have only x1. What are the consequences? We show that on the next slide. Okay. So here we are. Okay. So we have to make an assumption, okay, before you to see the impact or the effect of omitting something that should not be omitted. Now, remember, regressors are usually always related, as we've said early on. We just don't want a perfect relationship, linear relationship. So let's make an assumption. Assume x2 is related to x1 linearly. So we write a form of it like this. Okay, this v is not a v I wrote over there when I use the alphas. Okay, it's just an error term. So we make an assumption. If x1 and x2 are correlated, let's assume this linear. Of course, if they are not related and we cannot write something like this, then there is no problem from omitting x2. There is a problem if x1 and x2 are actually related and we can write x2 in terms of x1. So now let's go back to the population model and explore what happens. This is y, beta 0, beta 1, x1, and beta 2, x2. All this is x2. Remember, this is x2 plus our error term. Then we group like terms. Beta 0 is a constant. This times this is also a constant. This times this is a constant. So we group the constants. Then the coefficient x1 is factorized. We factorize x1, and beta 1 is attached to x1. Delta 1, beta 2, delta 1 is attached to x1. So you just group like terms. And then the errors are this and v times beta 2. So if group like terms, okay, you can solve this algebra, just group like terms, okay, factorize and so on. So what does this mean? This is our y, remember. This looks like a regression, a simple regression with only x1 as a regressor and some ugly constant and ugly error term. What is the point? Whenever you run a regression of y on only x1, like our erroneous model was suggesting here, okay, the erroneous model says just run a regression with only x1, okay. So this shows that if you run a regression y on only x1, you are not actually getting beta 0 hat. You are going to get something in addition, beta 0 hat plus beta 2 hat, delta 0 hat, something like that. So in other words, you are not getting beta 0 hat. You are getting something else, which is biased. It's beta 0 plus something. So it's biased. Similarly, instead of getting beta 2, beta 1 attached to, right? This is what you want. You want to get a coefficient of beta 1 attached to x1, but you are actually getting something ugly. It is also biased. You are getting beta 1 plus something, beta 1 hat plus something, so an estimate of something other than beta 1. So it shows bias. That's the consequence. All estimated coefficients will be biased. if you were to omit a relevant variable. Okay, the linear form is assumed to make the mathematics easier, but it shows what our conclusion. When you omit a relevant variable, the regression coefficients are biased, okay? But your sampling variance may not be affected. So it's like the opposite. Okay? The sampling variance may not be affected. Okay, but under the adding irrelevant variables, that one too is the opposite. The coefficient will still be unbiased, but the variance may go up. So take time and get the difference, okay? Over here, the coefficients are biased and the variance will not be an issue. It will not be it will not be bigger. Okay, the variance of the estimates, beta 0 hat, beta 1 hat, beta 2 will not necessarily be bigger. But the effect is that coefficient will be biased. The opposite happens over here. Here, we are not concerned about bias, okay, because in the population, this is actually 0. We are concerned that we've added another term, which is irrelevant and may increase the sampling variance. Remember that, okay? I like this question, asking the consequence of irrelevant variable, consequence of omitting a relevant variable. Assumption number 4, I already explained this in simple regression, so I don't waste time on this. The idea of homoscedasticity, that the variance of the error term, okay, given the regressors is constant. Okay, that's homoscedasticity. When this is violated, then we have heteroscedasticity. Okay, you remember that in simple regression, we derive, okay, you remember that in simple regression, we derive the variance of beta 1 hat to be sigma squared over sum of xi minus x bar squared. So here I do not go through the pain of deriving it, but I should write down the final result. Okay, here we had only one regressor, so one slope parameter. Here is tedious to derive, so we shall skip it. If it becomes necessary, we'll derive in class. Remember, there are beta 1 all the way to beta k. So the variance of one of them, let's say beta hat j, one of them will be sigma squared, quite related to this. SSTJ 1 minus r squared j. Please pay attention to all the terms. Of course, this is the variance of the error term, so it's straightforward. This is also similar to what you know already. Okay, there's total sample variation in the explanatory variable xj. Remember, we are talking about one of them, xj. So it must be the xj. The xj must be the one attached to the variable j. So we want to see the variation in the variable xj. Okay, is xj having a lot of different numbers, 1, 4, 5, different values, or there's no much variation? Maybe they are all 2, 2, 3. No, we would like to see the variation in that variable. So that's the total sample variation. So that's it. And 1 minus r squared j. Pay attention, this r squared is different. It comes from regressing that variable xj on all other regressors. The other regressors, let's say beta 1, x1 plus beta 2, x2 plus beta j minus 1 x j minus 1, because I don't have the j. J is the one we are working with, so you skip and go to the end. Beta k x k plus an error term. So run that particular regressor whose coefficient we are interested in. You run it on all other regressors. Then you collect the r squared from this regression. That is the r squared j here. It is not the r squared coming from y regress on the x's. No, it's the particular xj regress on all other regressors. So that is this r squared from a regression of explanatory variable xj on all other independent variables, including a constant. So that's the formula. Remember it, we will need it. It's not hard to remember. Okay. Okay, let's go on. So this slide just analyzes the components of that formula, the sampling variance, that the variance of each beta j is what? The variance of the error divided by what? The variation, okay, in the xj variable, then 1 minus r squared j. So we are just going to be comparative statics, that when the numerator is high, the variance is high, and we don't like that because this is noise of the error. So when error noise goes up, the whole noise, okay, of variance of the estimator beta 1 hat also goes up. So we don't like that. That is the description here. Okay, that's the first one. The second one says that if there's much variation in the x's, it is a good idea. In other words, if this increases much variation in the x's, okay, there are different numbers, rich information with variance, good variation, then it is good. Why? Because it is increasing the denominator. If this is high, it's increasing the denominator. Okay, if these are constant and the denominator increases, the whole quotient will fall down. That means your variance is falling, and that is good news. Okay, you don't want a wider variance and so on. So that's a description here. Take your time and read that. Then finally, on the next slide, we'll be talking about this one. If this r squared j goes up, it means xj is highly related to its other x's. Remember, this r squared j is a regression of xj on all other regressors. So if this number goes up, it means xj is related to its other regressors, highly related. What happens if r squared goes up? 1 minus r squared becomes a small number. Let's say 1 minus r squared. Where's my pencil? So think about it. If r squared j increases, it has one meaning, that x is highly related to its fellow covariate. Now, when it goes up, then 1 minus r squared j will go down, will become smaller, because you are subtracting a bigger number from 1. This is big. When this is big, it means it's also close to 1. So 1 minus a big number will fall relative to if r squared j were to be smaller. So if this thing is falling, let's say it falls as slow as 0.1, then you are 0.1 as you are taking a tiny fraction of this. You are taking a tiny fraction, right? So if this becomes small, then you are taking something like 1 minus r squared j is 4. Let's say it falls to 0.1. Okay, so you take a tiny fraction of this. A tiny fraction of SSTJ will also be small. So the whole denominator is small. The smaller the denominator, the bigger the whole quotient. So here too, we don't like it. The whole quotient will go up. That means the variance is going up. We don't like it. Okay, so that means that we don't want r squared at x to be so much highly related to other regressors. Some correlations are allowed, but if it's so high, there is a problem. It increases our variance. Okay, the sampling variance of the estimator. So that is what is discussed at part 3. Okay, take your time and read that here. Linear relationship among the independent variables. Okay, you regress SG on all other independent variables. The sampling variance will be higher, as I've shown you with the comparative statics. Okay, the problem is called multicollinearity. If r squared j is very high, approaches 1, it means SJ is highly related to other independent variables, which is causing an increase in the sampling variance. That problem is called multicollinearity. Okay, I'm saying that we don't want a perfect collinearity. That has been ruled out. We are saying some relationship or correlation is allowed, but extremely high relationship where the r squared j is approaching 1 or r is approaching 1 is not good. And that problem is called multicollinearity. Okay, that is a linearly dependent, okay, almost linear. Okay, A perfect linear relationship, we don't want it completely. It's a no, no, no. We want small correlation. But if that correlation is not small and is so big that the x's are related, one x or two are highly related to others, that problem is called multicollinearity, okay? A near perfect linear relationship. So know what we mean by perfect relationship and multicollinearity. Multicollinearity is a near perfect. It is not perfect yet. And what are the impact? It increases the variance, okay, of our estimate. And that is not good, okay? We will soon see under inference. Okay. So because multicollinearity is a bad thing, there is a way we try to test it, okay? And remember the formula here. So we just isolate this one. 1 over 1 minus r squared j. R squared j. This thing here, 1 over this thing is isolated. It's called the inflation factor. Okay. So computers will generate that for you, and you can use it to make a decision. It's called, it is what is inflating the variance, right? So we call it the VIF, the variance inflation factor. Okay. It's an arbitrary rule of thumb. Okay. If this number computed by a computer is greater than 10, in some books they say 5. If it's bigger, then multicollinearity is a problem. What is multicollinearity? When there's a near perfect relationship, okay, between or amongst your independent variables or your regressors, that causes increase in the variance of your estimates. Okay, so under the assumptions we've enumerated so far, linear in the parameters, zero conditional mean assumption, variation in the axis, and homoscedasticity, we know that our OLS estimator is efficient. It means it has the smallest variance. We can show that it is unbiased, which we did under the previous lecture, and so on. So here also we have the blue, okay, under the Gauss-Markov assumptions, okay, which we've just discussed. Okay, so under the Gauss-Markov assumptions, which we've just described, the first one is what? Linear in the parameters. Okay, let me go back to them as we summarize. Assumption number 1 under multilinear regression. So some of these are not in the simple regression. Okay, so first, linear in parameters, you must remember this. You can be called upon to list the assumptions and explain them. There is no perfect collinearity. This couldn't have applied in simple regression because there was only one regressor. Okay, so 1, linear in parameters. 2, no perfect collinearity. And then 3, this zero conditional mean assumption. And then 4, homoscedasticity. Some books add some on it and so on. But just understand that in any regression, we want our error to have zero mean, constant variance. That's homoscedasticity. And then linear in parameters is always there. The error should not be related. No perfect collinearity and so on. Even some books assume no multicollinearity. But just get your basics like the 4 here and be able to explain them, in addition to the error having a zero mean and the errors not being related. Okay, so that's the end of the lecture. We'll meet in class. If you have any questions, we will address them. Okay, thank you. Have a good day. Bye.